So last time we looked at Markov decision processes, which are a way of modeling decision-making problems, particularly ones under uncertainty, but we never got around to talking about how you actually solve them. So we just looked at them as a modeling tool, and today we're going to look at an algorithm called value iteration, which is how you produce action decisions from those decision processes. So we're going to go back and look, I think to start with, maybe recap what a Markov decision process is. And when I say that, I'm just going to say MDP. So that's the abbreviation. So I will say MDP from now on. And we've got this. So this is the model we had from last time. So this was the sort of transport or getting to work MDP. If you're thinking about just the average cost, then everything gets a lot easier. I made a slightly fancier version this time. So you start at home. Your goal is to get to work. And you've got effectively 3 action choices. You can choose to take the train, you can choose to take a car, or you can choose to go on your bike. And this is a way now we can start to think about the more formal way of thinking about the MDP. So an MDP has a set of states which describe it in this model, they're kind of the locations you can be in. But in general, they're sort of like a snapshot of the world. And we think of these, we typically write big S, capital S for a state, and we say the lowercase, some state is an element of this set. In this example, our states will be things like at home, in the waiting room, on a train, in the car, in different traffic levels, or at work. And then we've got actions. So the actions are the choices we can make. And we usually label them A, out of some big set there. And here, the actions are things like take the car, take the railway, cycle. We've got a drive action, relax, wait, and go home. So these are all be in the previous video and explained it a bit. And then the kind of interesting things that we're modeling, we've got costs. Sometimes people would use rewards interchangeably. And the costs are going to be how much it costs to execute a particular action. And we're going to have what we call a cost function, which is going to be CSA. So I think about the cost of executing some action A in a state S. And then I have my transition function, which is going to give me the probability of ending up in a particular state after executing a particular action. So you would write that typically with a T, S, A, S prime. And the S prime is the successor state, the state you get to. And so if we look at, say, the model here, we've got our home state, our action car, and then we have 3 different S primes, so 3 different states we could reach. So this is light traffic, medium traffic, and heavy traffic. Those are all different states. And so the states are the circles, right, in that picture. So this is our MDP. We kind of assume we know this model. We assume we know our transition function. You could also think about this transition function actually as a sort of conditional probability. So typically that's going to be the probability of being an S prime given that I started in state S and I execute action. So this is kind of an equivalent way of thinking about it. So this is on our edges, these are the numbers after this dot. And then our costs are the things we've got after these colons. So that tells you, that's kind of the pictorial version of this. Right. Clear so far?
Yeah, I think so, yeah. So just as a kind of overview, if I took the car, there's a possibility that the traffic is heavy and therefore the time that it takes is our cost in that instance. It's going to be longer, right?
Yeah, but the way we've modelled it here is when I get in the car, this is just kind of a quirk of how you have to model things in an MDP. It's not always obvious the right place to put the costs. Mm-hmm. So here we have this intermediate state where the state is kind of effectively being on the road in light traffic or being on the road in medium traffic. And then we have one action drive, but I can execute it in any of those states. Yes. So it's the same action, but when I execute it in different states, it costs me different things. So when I execute the drive action in the medium traffic state, it costs me 30. And that's why if you look back to this function, it's both kind of an S and an A in the cost function. It's like, okay, I'm executing this action, which might be drive, and then this could be light traffic, LT. This is a decision-making model. What we want is action. So the reason you've got an MDP is because ultimately you want to get some action choices. And the way we describe this, or the way we kind of encode the actions, is in a policy. So policy is the output. When I say solve an MDP, people talk about solving an MDP, they're solving it to produce a policy. So a policy, we're going to represent with pi or p. If I put in a state, it's going to give me an action back. So you can think about this as a lookup table or a map. The input is the state, the output is the action. And when we solve our MDP, we get a policy out. And so that's really the key thing. And we'll probably want, well, in this case, we're going to want a policy that covers all of the states in our problem. So then the question is, what policy do we produce, or how do we think about this policy? In the research that I do, we think about the policy as being produced to meet some kind of specification, which is kind of some set of requirements you've got for solving the MDP. In our case, for this example, what we want to do is minimize cost, right? We want to minimize the travel time to work, and therefore we're going to minimize this cost function. In fact, more specifically, we're going to minimize the cost function to reach the goal. Typically, we might have some state that's an element of a set G, and G would be our set of goal states, and that can be more than one state. And for this kind of MDP and the work that I do, we think about typically achieving goals, because that's an interesting way to think about the world. But there are other solution mechanisms and other people that think about MDPs that think about things like reward, and they might do reward maximization rather than cost minimization. And often in things like reinforcement learning, people think about infinite horizon discounted reward maximization, which is like your system's going to run forever, and I just want to kind of maximize the amount of reward I get for the next 5 or 6 steps, but doing that over an infinite horizon, so I keep kind of pushing forward.
Just continuing and continuing, yeah, okay.
And there's other things as well. So you can think about specifications such as, we could represent a specification as something called temporal logic, that instead of just describing a set of states, it might describe a sequence of states or a conditional sequence of states. So one of my students loves this carpet puddle example, where you say, I'm a robot in a home, and if I drive through a puddle, then I have to go over the carpet to dry my wheels before I go onto my charging station. And then you can also think about specifications that encode constraints. Say I want to reach work in a maximum of 60 minutes. That's going to change the set of options that I've got. And that constraint you can think of as a specification. Yeah. So I want to produce a policy to meet my specification. And there's a whole amount of richness that you can put into the specification, and that will change both the kind of algorithms you need to use to produce the policy and also the kind of behavior you get at the end. We're going to, in this case, minimize the expected cost. So cost, we know, this is this C that we had earlier. Cost is a random variable. So this is a Markov decision process. There are probabilistic outcomes to our actions. If we go back to this car example, when I get in the car, I have different probabilities of reaching these different states, traffic levels, and then each traffic level yields a different cost when I execute the drive action. So if I was to say, what is the cost of driving, there isn't one answer, there's a distribution of answers, and each answer, each cost, has a different probability of occurring. And the expectation you can think of as like the average given the probabilities. So the expectation of a random variable is the sum over its outcomes, so its costs, where each outcome is then multiplied by its probability. If I say, like, what's the expected cost of, I'm not going to be too tight on the symbols, what's the expected cost of effectively taking the car, of the drive action? Well, it's the probability of ending up in the light traffic times by the cost of driving after the light traffic, plus the probability of ending up in medium traffic times its cost, times which equals 32. I'm not a professor of basic mathematics. My kids could do that, but I can't. So that's the expected cost of the car action. And there's some interesting properties about this model in particular, which in this case, the expected cost is kind of close to the most common value. But like the worst case cost is a lot higher. But I think today we won't go into that, but that's an interesting property of using the expectation. Yeah,
because I think you said before, if you had to get there within an hour, then even the finest, minutest chance of it taking longer than an hour is a problem.
Yeah, exactly. We wouldn't want to use the expected cost as the specification. We'd want to use some kind of bounded cost specification that prevented these outcomes from ever being considered. But for the algorithm we're going to look at today, we're going to stick with expected cost, and we're going to be looking at minimizing these kind of values, or explicit these kind of values. This is kind of the basic, in some sense, that's kind of the core mass that we're going to need to think about. And now we need 2 more steps. We need to think about how we write down the value, or how we generalize this kind of approach to a policy, because the policy is the thing we're trying to produce. And then we need the algorithm that's actually going to create the policy to minimize these kind of values. Next step is to think about how we take that expected cost and write it for a policy. The way we think about this is we think about what's called the value, and I'm going to use V for value, and we can think about this as generally it's called the state value, which tells me effectively how good or how bad is it to be in a particular state in my MDP. And it only really makes sense to think about that when I've got a policy. So I'm going to say, what is the value of a state under a policy? And I'll write that as V pi of S. And so that's going to say, if I'm executing this policy, or I've committed to using this policy, how good is it to be in a particular state? And this is going to be, the number of this is going to correspond to the expected cost of following that policy from that state. So it's saying, okay, I'm in this state. If I follow this policy, what's the expected cost to reach the goal? If I'm already in my goal, what is the expected cost to reach the goal?
0.
Oh, you're good. You're good. What we'll do is we'll define this function, and it's 0 if the state is an element of that goal set that I wrote earlier. And that kind of gives us a nice fixed point to think about when we do the maths later on. We're going to work backwards from there, effectively. And then if I'm not in that state, then I need to choose an action, effectively, that minimizes that cost. And the way we write the cost of an action is something called the Q function. And the Q function is the sort of, we'll call it the action cost or the state action cost. This is going to sort of come back to the expected cost of executing that action we talked about previously.
And just to check, because I know you mentioned the pi symbol before, but this is nothing to do with pi as we know with circles and everything like
No, nothing to do with circles. Pi is our policy.
Yeah. Okay.
And because policy starts with P, we could just write P there, but
it's pi, right, okay.
Computer scientists like to be fancy. So that's why it's pi. So we'll write the Q function for S of A, and the value here, because we're trying to minimize the expected cost, we're going to perform a minimization over A. So the value of the state S under policy pi is either 0 if I'm in the goal, otherwise it's it's the value I get if I choose the best action in that state, or the best action that I know about, according to this policy. So all we have left to do now is define Q. So QSA equals the cost of that first action. So whenever I execute that action, I always have to pay this cost. So whenever I get in the car on this model, it costs me 1. Or whenever I cycle, it costs me 45. But that's only the kind of immediate action cost. Mm-hmm. We also need, because this is the policy, and it's the policy to reach the goal, I have to also include the subsequent steps.
Yeah, okay.
And the way I do that, if we look at our car example, there are 3 different states I can reach with different probabilities. So this is where I effectively put the expected cost of following the policy from this state. That has to involve a sum over the possible successor states. So this will be our S prime. And it's the probability of being in that state. So again, we think back to that expected value statement. It's the probability of being there. And in our MDP language, that's T, which is our transition function, S prime. And then we multiply it by the value of being in that successor state. So the value of that successor state is V. It tells me how good it is to be in that particular state. But now this is for the subsequent state. So if I'm in home and I execute car, S prime might be light traffic. And if it's light traffic, then it's 0.2 multiplied by 20. And I'm summing it up across those just like I did for the example with the expected cost. So now I'm doing this sum. So this is our little sum symbol. Doing a sum over all the successor states. And this is it. So these are called the Bellman optimality equations. And actually, the reason they're called Bellman optimality equations is typically we think about the optimal Q values and the optimal V state values. And we'd put a little star at the top to say they're optimal. But here we're just sort of talking generally about the values under a policy. Right, so that gives us the language to understand state values and state action values given a policy. The remaining question is, how do we find the optimal policy? How do we find the best policy? And the best policy or the optimal policy for us is the one that's going to minimize the expected cost to goal. We can think about that as our expected cost of following the policy. And our expected cost to goal is just going to be this minimization step, right? We're going to find the policy where for each state we minimize the value and we choose the best action. The policy is going to be a mapping from the state to the lowest Q valued action. So how do we do that? Well, the interesting thing, I don't want to mix up your pens. Well, okay, maybe go on then, I'm going to do another color.
Somebody stole my black, but otherwise
Okay.
you can use any colour you like.
So we have an interesting problem. The interesting problem is Q is defined, or V is defined in terms of Q, and Q is defined in terms of V. So like these things rely on each other. There's kind of a recursive definition. So the way we solve this is by something called dynamic programming. So dynamic programming is kind of an iterative technique that allows you to compute kind of one set of values, and then you run the algorithm again using the values from that previous iteration in the next iteration. And there's lots of different dynamic programming algorithms for different problems. The sort of dynamic programming approach for the Bellman equations for MDPs, that approach is called value iteration. And value iteration is an algorithm that simply computes the values of the states at one iteration and then repeats that, and it repeats that and repeats that until you found the optimal policy.
So you've got to, do you create a graph or something and have a look?
No graphs. Actually, that's interesting. So there are, generally you can be more efficient if you start thinking about graphs and connectivity, but all of the algorithms that use graphs typically, they're what you'd call approximations. They're an approximate version of value iteration. Right. They tend to only focus on like a subset of the problem. Here we're going to do like the full mathematical, optimal, exhaustive version that gives us the true values and the true optimal policy. But in reality, it works really well for small problems, but doesn't scale particularly well.
Right.
So
it's like brute force almost.
Yeah, it's absolutely. It's the brute force version of this. It's not particularly smart, but it's mathematically correct. So the kind of key thing that we're going to do in value iteration is we're going to compute a set of values at Vn. So when I'm going to here, I'm sort of mixing and matching my symbols a little bit. Previously I had a policy here. Now this is n is going to be the iteration of the algorithm, so the number of times we've gone through the loop. And we're going to use the values we've computed at Vn in the calculation for the values at Vn plus 1. So, and this is going to be the way that the dynamic programming kind of process works. It takes the previous values and uses them at the next time. You could write this in a single line that makes it a bit clearer, but I think the algorithm will, I hope the algorithm will be clear enough. So, how does this work? Well, we start at V0, and we're going to initialize kind of with arbitrary values, which is effectively we're going to give random values to all our states because we don't know them yet. Typically, because 0 we know is the goal state, if the states are in our goal set, which we know, we're going to initialize them to 0. And for this example, if our states are not in our goal state, we're going to initialize them to 100, because 100 is a big number. And it's bigger than any number in this, and it makes the maths a bit easier. You'll write the algorithm out, and then I'll come back and do the maths. So we'll come back to those numbers in a minute. We basically just repeat the algorithm. I'm going to see if I can fit this in. Let's see. What we do is we compute for S in S, so for across all our states, we're going to compute Vn of S. Here what I'm going to do is we could sort of write the kind of whole Q thing here. We're going to minimize A, and this is going to be over CS of A plus the sum over S prime, T, SA, S prime, multiplied by, and this is the interesting thing, V of n minus 1 of S. I've kind of rolled the two equations. So if we go back in here, I had two things. That's why I kind of hesitated a little bit on that. When we compute our value, it's either 0 if it's the goal state, or we do this minimization over Q, and Q is like this. I'm just going to be lazy and write that all in kind of one line here. So we're going to compute the values. If state isn't the goal, we're going to do this. If state's the goal, it's 0. We'll ignore that in the algorithm. So your viewers shouldn't type what I'm writing here into a computer. They should think about it a bit more before they do that. So we compute the values, but the key thing really is in this bit here, where we're using n, and we're calculating it based on n minus 1. So we're using the values of n from the previous time, and we might even, if we want to up here, we can start with n equals 0, and then in this loop, we're just doing n equals n plus 1. So each time we go through this, n is going to increase. And so the first time round, we compute the kind of v, the first, that would be 1 of s using 0, and 0 is going to be our v0 that we initialized before. So we do that over all our states. That gives us the state value actions that we want. So we compute our value, and then we also compute something called the residual. We'll calculate something called the residual. The residual is the size, or the absolute value of the difference between Vn of s minus Vn minus 1 of s. So this residual tells us how much the value has changed in each iteration. So we compute our value, and then we look how much has our value changed. And so this is going to be the residual of s. We do this for all our states, and we repeat. We're kind of repeating while the max of all the residuals we've calculated is greater than some epsilon. So we're going to run this loop until the difference between values at each iteration is smaller than some small value. And epsilon kind of, it's problem dependent, much like the initialization, but that might be, I don't know, 10 to the minus 5 or something. We might want a small number, something arbitrary. And this is all we need. So the kind of core bit is the mass that we saw before, which is computing the value of this state. We look at how much the value has changed at each iteration, and then we run that until the changes across all our states goes below some small threshold. So I think the thing to do now is just to work. I can just kind of go through that for this example, like 1 or 2 iterations.
Yeah.
I'm not gonna run forever. And then I think that's kind of enough. I might use 2 pages at once.
Yeah, why not? Yeah.
Let's do that. So let's have V0, and maybe up here I'll keep the values, and down here I'll do my very bad mental arithmetic, or not even mental, arithmetic, full stop, and try and work out. I'm going to write all our states, and I'm just going to abbreviate them. So we've got home. So those are the states in the problem. I said I will initialize all our state values to something kind of arbitrary. So work we initialize to 0, and everything else we'll make 100, because I don't know what it is. We'll do explicitly the kind of minimization step that we had in the middle. It's sort of a bit easier to work bottom up, and it's easier, at least mathematically, to start with by thinking about the actions that are kind of deterministic. So we'll start with the action of cycling. So I can only execute cycle in home, so I'm going to say, what's the Q value of being at home and cycling? Well, it's the cost of cycling, which is 45, plus this expected value of following the policy after that action is complete. But cycling takes me with probability 1 to the goal, so there's nothing to add on there. So I am just going to write 45. So I know the Q value of cycling from home is 45. Well, we've also got relax. So relax is similar. So relax is deterministic. It takes us to the goal. It costs 35. So I might just write the Q value of, here I'm on the train, and if I relax, that's going to cost me 35. That's reasonably easy.
So remind me of relax. Was that you just get straight on the no?
That's when you're on the train. There's nothing to do. There's no more decisions to make. You're happy. You just sit there, and it takes you to work. The train side is interesting because you might
have to wait to catch the train.
Yeah, when you get to the train station, you either get straight on the train with probability 0.9, or you go to the waiting room. Yeah. And in the waiting room, you can either choose to carry on waiting, or you can choose to go home. Let's do the waiting room. So the waiting room, I have 2 options. I can either choose to wait, or I can choose to go home. So let's look at the go home action. So if I say the Q of being in the waiting room and choose the go home action, well, okay, go home costs me 2 to execute, and then I've got one outcome state, which is being at home. So this is going to be our kind of Q of in iteration 1. So I need to add on the value of iteration 0. So we've got this sum, but there's only one state, which is the state of being at home. There's only one outcome state from that action. So we don't really need the sum. the value of 0 of my successor state, which is being at home, or just h from the thing. So the value here, from 0, I go back to this table, I say, okay, this is 100. So the Q value of being in the waiting room and executing go home is 102. I've got this other option. If I'm in the waiting room, I can choose to wait. And this is where things get a bit more interesting. And I probably have to do some maths, although I think I know the answer. I did do the maths earlier, so it looked like I knocked it off the top of my head, and that's making it harder because now I'm like, oh.
Which bit was which?
Which bit was which? I don't know. Yeah. So I'm in the waiting room, and I can choose to wait. Now, so the cost of waiting is 3, but I need to add to that. So now I'm going to do this sum bit. So what I've got is I've got the probability of there not being a train, which lands me back in the waiting room. So I multiply that by the value of being in the waiting room from the previous iteration, which is 100. And I also add on the probability of there being on a train. So the train value here from the previous iteration is 100. So that should give me 103, because those two have the same outcome value, 103. Now I can minimize, because I've got my two actions. In my waiting room, I can either go home or I can wait. The waiting action costs 103. The go home action costs 102. So now, if we go up here, we can start filling in the next iteration. So value of being in the waiting room has gone up, and our residual will be 3, the difference between those two. So where else can we look at? I think now it maybe makes sense to think about the railway action. If I'm at home and I choose railway, so commit to the railway, that's going to cost 2, because it cost me 2 here. And actually I have the same choice as the wait action. So with point 1, I'm in the waiting room. Point 9, I'm in the train. So we've already done this mass up here. So it's the same as that. And then at the end, it's going to be 102, because I only cost 2 the cost of the actual action is only 2. So then I've got the value of being rail, cycle. So that's 2 out of my 3 home actions. So let's look at our final home action that's applicable in the home state, which is to take the car. So the car cost me 1, I guess, because it's sat on my drive. It's easy to get to. And then it's 0.2 times the value of being in light traffic, which again, from our previous step, is 100, plus 0.7 of being in medium, plus 0.1 of being in less. So again, actually, this is fine, because this will be 101, because all of these will sum to 100, and we got 101. So now I've got 3 actions for home. I've got getting in the car, 101. I've got getting the train, which is 102, and I've got cycling, which is 45. So we can minimize over those. Which is the lowest?
Cycling.
Excellent. And so we can say the value of being in home, and this is for this iteration, is 45. So we've calculated the value for that. What else do we need? So the rest we can kind of fill in more or less directly, I think, from the answers. It's from what we know from the model. So the goal is always 0. And all of these other ones where there's just one deterministic action, so one action with no distribution of the outcomes, it's just the cost, it's just the immediate cost. So it's going to be 70, 30, 20, and 35. That's kind of one iteration of value iteration. Probably not the most riveting video, watching a grown man do maths on a bit of paper. But it kind of gives you an idea. The key thing was that we started with these arbitrary values, and now already some of these values are correct in kind of the final value of being in that state. In fact, anything from here on down, where there is a deterministic route from that state to the goal, we've actually converged in one step. But we still have quite a big residual. So the biggest residual I think we've got is here. So the max residual is 80. So we can't stop. We would run another iteration. But now if we went on to doing this for V2, right, the mass would start to be a bit different, because we're using these values here before we calculate the next thing. Right, so we made a mistake. We made a mistake. I made a mistake in that for waiting room here, we're at 103, but I should have been minimizing over both these two, which is 102. So that's going to be a 2. So we can look at the next iteration just to get a sense of how things evolve. And the important thing really for this problem is that at the next step, there's kind of 2 interesting actions. So everything from train on down is kind of boring now. It's all converged. But for the next iteration, it's going to be these two values that change, and they change because the kind of the things they depend on, which is the sort of lower down states in this MDP, the things they depend on have changed in the previous iteration. So those changes now kind of propagate through. So this is the value iteration or the dynamic programming at work. We've changed these things, so the things they depend on will then change subsequently. And I'm just gonna scribble on top here. But now we know that, so if we're gonna move this to now kind of Q2, so for V2, these values are no longer 100. So this was light traffic, which is now, this is gonna become 20, this is going to become 30, and this is going to become 70, and then this will become 33, I believe. And so that means that up here, we will get 33, because 33 will be better. So the rail action, now I'm reading this off another bit of paper, this becomes 44.7, and ultimately will converge to something a bit lower. But 33 is the cheaper one, so we're going to end up with 33 here. And everything is going to effectively, after this point, start to get cheaper and cheaper. So, in fact, at some point it becomes better to go home. And I think at this point it probably becomes better to go home. So I don't know the exact number here and I won't work it out. But in the final policy, the best action for waiting room is to go home. So the optional action is to go home, because once you're home, you then take the car. So we can also look at what the optimal policy is, and the optimal policy is the action choice that gives us the minimal values here. So although I've not shown it, the optimal action choice for the waiting room is to go home, and then the optimal choice in the home state is to take the car. So in the end, we would say that the kind of sort of a bit messy across here, that we've got the optimal value, so we'd put a star. The optimal value being at home is 33. And we'd run this, I think, you maybe run it 2 more times, then the residuals go to 0. And then what we do to get the policy is we pick the actions with the minimal Q values.
And residual, just to remind me, is the difference between one iteration to the next?
Yeah. Yeah, so here when we went from 0 to 1 of the iterations, we look at the absolute difference between the 2 columns. And then we take all of those residuals that we calculate for all the differences have to be below some threshold.
And you're basically culminating an answer that can't change anymore, is that right?
Yeah, exactly. So the kind of maths that underpins this, the dynamic programming maths, says that there's a kind of a fixed point to this set of equations, and value iteration is the algorithm that gets you to that fixed point. And for big complex systems with lots of stochasticity, lots of kind of probabilistic outcomes, it might take a long time for those things to converge. And you might not care about the exact values of those things, so you might not have a very tight threshold. But yeah, in time, those things value iteration will converge to the fixed point of the Bellman equations.
And they should always pretty much get to a certain point, or can they go crazy and never do that?
Oh, no, absolutely, it's guaranteed.
Oh, right.
Well, okay, so
depending on the model.
It depends slightly. So in this case, for what we're doing is minimizing expected cost to reach goal. We're solving something called a stochastic shortest path MDP. And when we do that, we have to have a certain set of requirements on the model, otherwise value iteration won't converge or will give us some weird results. So those are that there are no zero cost loops. So it can't be possible for me to choose an action that changes my state but costs 0, and I'm not allowed to then go back for 0 cost. Otherwise, there's a chance that I could basically keep choosing those actions.
You get stuck in a loop.
I get stuck in a loop. So like the algorithm doesn't get stuck in a loop, but the policy wouldn't be valid. The policy wouldn't reach the goal. And the other requirement is that you must be able to reach the goal with probability 1 from any state in your model, for that to be a valid stochastic shortest path and for us to be able to use value iteration. So under the right conditions, the algorithm always converges. And largely for a lot of problems, so I work in robotics, a lot of robotics problems we think about have that property. Well, let's say some robotics problems have that property, or you can convert the problems into problems that have that property. If they don't have that property, then you have to do other things. You have to process the model, or you use a different algorithm. And really, in practice, I mentioned earlier, people use value iteration for small-ish problems. But then small might be orders of, I don't know, hundreds of thousands, maybe millions of states still. So very big problems in terms of the kind of things we're looking at here. But beyond that, things get very, very difficult to solve. And they get difficult to solve. I mean, maybe it's worth just trying to illustrate that a little bit. So if I can think about the computational complexity of one iteration through value iteration. So what did I have to do? Well, I had to look at every state. So if we go back to our previous notation, I had capital S. And I actually have to look at, in these kind of, if I look back here, I've got this, basically within this for loop over every state, I need to look at every successor state somehow. So there's this kind of, basically a quadratic thing going on here saying, I basically have to look at, for every state, I have to look at every other state. And so that means the kind of complexity is the number of states, so the size of that set squared. And then I have to do that for every action. So I kind of went through every action in a bit of a random order here. So I need to multiply that by the size of the action set. And so the computational complexity, so the kind of big O notation, and that's one iteration. So that's just one loop through this algorithm. And you can't tell in advance how many iterations you're going to need. And so this, as your states and action spaces grow, this becomes quite costly. The other issue is that what I have to do is I have to build this table. So I have to write down every single state. And so if S is hundreds of thousands or millions, then these tables get very big. And typically I have to produce matrices to encode these things that have the number of states on each dimension. So it's a 2D matrix. And that again gets very, very big. So often it's the cost of kind of writing down and then iterating through all these states that is the problem. The algorithm is kind of simple. It's just linear algebra, it's maths. But like the cost of writing everything down, enumerating the states and then storing all in memory is what typically drags these algorithms down. So now car is going to take 1. This is me leaving the house and going to my parking space and finding my car. Railway, maybe I have to walk a bit further to get to the railway, so that'll be a cost of 2. And then we can start to put these actions in. So actually these arrows should be dots. And I can put in the action that we had before.